think I got it wrong. X plus 2, X minus 1.
Alright guys, let me catch up to you. How many changes in sign do you see the way it is?
This one's first. That's my problem.
It's just
Alright.
pretty much.
So you see 1.
If you see
So what does that mean?
that's gonna change. Even hours.
There can only be one. There can only be one positive real. So we know if you find one positive that works, what can you do? You can throw out all the other positive ones because there's only one positive real root. What is p of negative x? How many changes in sign do you see there?
3.
Yeah, 1, 2, 3. Cool. So what does that mean? There could be
3 negative real roots. 3 or 1.
3 or 1 negative real roots. Like, so there could be 4 real roots, or there could be 2 real roots and 2 complex roots. Right? That's the possibilities here. There's got to be a total of 4 answers because it's a 4th power. It's kind of nice. So what about part B? What are my possible rational zeros? Yeah, all the factors of 8. Now I'm kind of, no, it's not 3 yet. I'm kind of being a little nice here on purpose. I want us to get the process down. The next level of this would be for me to put a number there, and then you have to make all the possible ratios with all the factors of whatever number is there. So you can imagine if I put a 20 there, that would suck a lot, because then you have to make all the ratios like 1 over 1, 1 over 2, 1 over 4, 1 over 5, 1 over 10, 1 over 20. Those are all possible.
Plus or minus.
Plus or minus, exactly. Yeah. You with me? And each of those would have to have that. Now some of them will reduce to the same thing you already have, but not enough of them as you'd hope. Okay. But the process doesn't change. You can still check the fractions out in your little penalty box like you would any number. The minute you bring fractions in though, that just makes more chance for us to make mistakes. So what did you guys try first?
Negative 4.
So if you try -4, and it comes out to be a lower bound, you can at least throw out 8, right? It might not be a bad place to start. Anybody start with positive roots?
I start with positive.
Since there's only one possible positive real root there, the minute you find it, you can throw out all the other positive ones. That's sort of promising. And think about this too. If you tried out 2 negative roots and neither one of them worked, then what situation must you be in? There can only be one negative real root. There must be a couple of complex then, right? Because there's either 3 or there's 1. Do you start to see how these things give you boundaries that kind of help you cut the problem down as you go? So I don't know. Let's try. The most emphatic one here was -4. So we got 1, -6, 7, 6, -8. Well, I'm looking at the wrong. 1, 6, 7, -6, -8. There it is. Not this chapter. So now you bring that down. Is this going to work? Let's see. -8, -1, 4, -2, 8. Sweet. So what do I know so far? Yeah, I know that this thing equals x plus 4 times.
That it's x cubed plus 2x squared minus x minus 2.
Now, guys, here's what I'm hoping somebody somewhere did. I don't know if anybody got to this point. You only do synthetic division when you can't just directly factor the damn thing, right? I am never going to make you continuously do. So at the very least, the first step is going to be synthetic. Now, can anybody tell me anything about this thing? It's factorable. 4 terms, I can group it. You could do more synthetic. It's kind of nice because now the only possible things are plus or minus 1 or 2. So you can continue synthetic, but straight up factoring should be a lot better. You get an x squared minus 1, you're left with an x plus 2. And then this, I think some of you guys had this at the end. And of course that guy's beautiful little thank God from difference of squares. Some of you guys didn't like that at all. Okay? It goes slower. So this guy, how do you factor this guy? Yeah, x squared comes out. X plus 2 is left in. Take a negative out. If you want to, you can put a 1 there. So there's your x squared minus 1. And your x plus 2. And this guy, of course,
We got the same answer with this on the long route.
that's okay. Of course you're going to get the same answer. Synthetic division is not different. I could use quadratic here, couldn't I? Hell yeah. B is 0, A is 1, Z, you with me? I'm glad you're laughing. Quadratic, I could use it here. Why the hell would I? So that's my question here. I could use synthetic here. Why the hell would I? Synthetic is nice, but it should not be as nice as directly factoring something. That should be the best route always. Unless you really suck at factoring, which force yourself to do it then because you have to know it really well. Really soon. Now what do you notice about this? How many positive roots does this have? 1, like we predicted. How many negative roots would it have? 3. Like was one of our possibilities, right? Cool. The other thing that this could have done is it could have ended up with an irreducible quadratic. Irreducible meaning you can't reduce it except for complex numbers. With me, so you can still kind of do it with complex numbers. It would still work. Then you'd use quadratic formula maybe to break it down. Let me ask you this little side note. How do you factor that? This is called an irreducible quadratic. This is what I was just talking about. And when they say irreducible, it's sort of like the domain. You always assume that they mean over the reals.
You can take a negative out.
You could, but that wouldn't do anything for it. It still wouldn't be a difference of squares.
Quadratic.
Let's try it like this. If I solve this, won't they give me the pieces that I have to throw back in to factor it?
Yeah.
So you subtract 4, take a square root. What's the square root of negative 4? 2i. So it would be x minus 2i, x plus 2i. So you guys notice a pattern here. How do you factor x squared minus 49? X minus 7, x plus 7. And how do you factor x squared plus 49? X minus 7i, x plus 7i. See, the i's save you. You need two numbers that when you multiply, they're going to have different signs, but they multiply to be positive. And the only way you can do that is if you use non-real numbers. Because I squared is negative 1. It gives you the chance to change the sign to positive. With me? You can never factor a sum of squares over real numbers because different signs will always come out minus. But the i's save your ass because they themselves make negative 1, which brings it back to plus. Cool. And that really completes the whole thing because x squared plus 49 will look like this, right? 49 and up. Are there any real roots? No, so that's why it's got to be complex roots. Because they turn away from the x-axis. There's no way they can equal 0. No way they can have roots. Yeah.
For number C, do we just find the 0 or we find the...
We found both. We found the 0 is negative 4, so it makes it 0.
Okay.
Right? That's one of the zeros. And we also we were able to factor it. So what are the zeros for this thing?
Negative 4, 1, 2, and
Yeah. So those are all the numbers that you guys synthetically divided by and it worked, right? If you look back at what you did. force those work because those are the ones that actually end up being zeros of this thing.
Yeah, if this like not easy to factor, we just pick another number.
Exactly. If this came out, and trust me, not every four-term thing is going to be factorable by grouping.
Oh, we can.
Right? This one just happened to be.
Oh.
So don't think they are supposed to be. I don't want to make it sound like that. This one was, but I could very easily make this not, and then you have to use synthetic again. Okay.
We didn't use the lower upper bound.
Yeah, it didn't really show up for this problem because it was almost too easy of a
We
problem.
don't have like to use it, or
You don't have to, no. I mean,
But-
was my list, would you call this a very long list? Considering what it could be,
yeah.
this is not a long list at all. The problem we did earlier had twice as long as this. And the first thing we did was the upper lower bound, and that cut off half of our list.
Yeah.
So this is as long as that was after we cut off, so that's decent size.
So, yeah. Thanks.
Okay. All right. So to bring this all back, we've actually basically just finished chapter 3. Because what chapter 3 does, they do it in parts. It's all about factoring these polynomials. What could possibly come out when you factor polynomials? You might have some factors that require complex numbers. So they have section 3.5 where they discuss complex numbers. And then section 3.6 where they redo what they did in 3.4, but now they allow complex numbers to come in. Do you guys kind of follow me? So very often I will do this, and I just hope you can deal with this. I will lecture. I won't say where I am because they all kind of relate to themselves. And then what I'm going to do is what I'm going to do right now. We're going to go back and see if we can do some of the homework problems to make sure that you see what they look like. Because right now, if I'm you, I'm like, what the hell are they going to ask me in the homework? Should we be doing all kinds of shit up here? One little thing I want to do before we do that. Does anybody know how to divide complex numbers? Because I forgot how to. No. So for example, can somebody give me a nice example of a complex number?
I plus 1.
I like it. So we got I plus 1. Now somebody give me another one, a little more interesting. Not that it wasn't
Square
interesting.
root of 28.
Negative I.
That's not, maybe not that. Good.
Negative
I squared.
No.
I.
What's I squared?
1.
That's not complex enough. So let's do 8 minus 5i. Right? I know that's what you want to say. How in the world, a complex number, what form must it be in? So I'm glad that a lot of you guys seem to understand what form it has to be in.
A plus B.
It has to be in the form a plus bi. So everything before you talk about complex numbers, they are still a complex number, like the number 7, -2, square root of 3. Those are all complex, but they are with b equal to 0. So they're only the real part. Anybody here going into like electrical engineering possibly, or yeah, sweet. You'll know, and if you're not, just listen. One immediately nice application of this, because I always get the question, it's a very good question, what the hell use is complex numbers? They're imaginary. What the hell's up with you math people doing all this weird shit and making us learn it? When you get into electrical engineering or electrical physics or whatever you're doing, the real part and the imaginary part are the electric field and the magnetic field of one wave. Yeah, you know what I'm talking about. There you go. And you can get into, well, in engineering they use J instead of I. Yeah. But there's an immediate use for complex numbers. They keep track, and this isn't even the best use, but those parts of them keep track of that field for me, and the real parts keep track of that field for me. So at the end I can really see what's the field here, what's the field there. Okay. Cool. So it's a really good question, why the hell do we have these? One reason is because they just come out of the work we do. Right? It's really nice to have them so that if I have an equation with that power, I do have 5 answers. That's a nice, complete kind of idea. With power, 5 answers. Some of them might be not real. So, what's wrong with this currently? Does it look like a complex number? Does it look like a plus bi? No. It looks like a plus bi over a plus b. It doesn't look like a single complex number. Anybody remember how to?
Conjugate?
Yeah. You multiply by the conjugate. So I would multiply by the conjugate of what?
Bottom.
The bottom. So multiply by, what is the conjugate?
Plus.
Yeah, in this case 8 plus 5i. So of course overall I didn't do anything. Multiply the same things to the top and the bottom. It's a lot like rationalizing a denominator because I is a radical. I do be a radical. It's very interesting grammar. When we talk about complex numbers. What do you get at the bottom there?
8 squared plus 3.
Yeah, the middle term cancels, right? That's the whole reason we multiply by the conjugate. 64.
64.
And it would be minus 25i squared, but I squared is
Plus 25.
negative 1, so it becomes plus 25. And on the top, I just get, who knows, 8i plus 5i is 13i plus 8 plus 5i squared.
Minus 5. Minus 5.
Yeah, so I get 13i plus 8 minus 5, because I squared is negative 1. So plus 8 minus 5, so plus 3 over 89. So to make it look more like a plus bi, I get 1389i plus 3 over 89. So there's my a plus bi. I like the look on some of you guys' faces. So a couple things. Are we all cool with the fact that I squared is negative 1? So are we cool with that fact?
Yeah.
Hopefully your Math 110 teacher didn't leave complex numbers out. Because what is I defined to be?
The
Square root of negative 1. So of course I squared must be negative 1. How are we doing there? So what would I cubed be?
1. Negative 1.
I cubed, isn't that I squared times I? Right? Isn't I squared times I cubed? And what's I squared? Negative.
Negative.
So I cubed is negative I. What's I to the fourth?
1.
Good.
one.
Because that's I squared times I squared. Negative 1 times negative 1 is
One.
1. And then I to the fifth that repeats. I to the fifth would be I to the sixth would be negative 1, so forth, it repeats. You guys remember that, or have you ever seen that before?
Yeah, kind of.
It's kind of a side note. The most important thing is to realize this, because that happens the most. But the side note is interesting too, to note how the powers of I work. So here's how that works. If I had I to the 87th power,
You divide by 4, I think.
yeah, this would be I to the fourth. 4 goes in 87 how many times? 21.
20.
With how many left over? 3. I to the fourth is 1. And 1 to any power is 1. So this is I cubed, which is negative. Or negative. You kind of with me? So the remainder, actually, here's the quick way. That's how you kind of work it. But here's the quick way. The remainder when you divide by 4 is 3, which means you're the third step in the scale. I, negative 1, negative. There you go. You're at negative 1. The remainder tells you where you are in this list. The remainder is 1, it's I, 2 is negative 1, 3 is negative I, 4 is 1. Well, it couldn't be remainder
What
4.
does that look like a name?
The name.
The rule of I or?
Powers
Oh.
of I. Some really bad sci-fi movie. The powers of I. So that kind of rounds out section 3.5, yeah.
So it would just equal negative I, right?
Negative I. Yep.
Just by the way, like there's different numbers like I, like negative square root of negative 10 or something. Or just rounded to
You
I.
base those. How would you rewrite the square root of negative 10?
I
Isn't it the square root of 10 times the square root of negative 1? Isn't that true?
Yeah.
And what's the square root of negative 1?
I square root of 10.
So the minute you define I to be root negative 1, you've taken care of all negative roots. You can kind of take the negative out and write it as an I. Now, on one level, I hope you guys realize all we're doing is writing root negative 1 as I. It's like, ooh, good job, math people. We don't know what that is. We're going to call it I. Yay. You know, unfortunately, we picked an imaginary, which sucks because students normally don't buy into math too much already, and then they're like, well, now you're being honest, imaginary. That's right. So I'm like, shit, I have to pick the word imaginary. That sucks. But, and they did. There you go. Oh, you. Okay. So let's look at this homework real quick to see what you can expect.
This is for chapter 4.
Yeah. So section 3.3 is where we first talk about long division, synthetic division, or where the book first talks about it. We talked about it before that. 3.4 is where it starts to get a little weird. Yes? What's up?
Sorry, I skipped behind. It's the last step. I'm so lost.
The last step?
13 over 89.
Yeah, 13i over 89. Just breaking this up.
Oh.
Yeah. So now it looks like a plus b I.
Okay.
Because that's the form of a complex number.
Okay.
Let's see, what was this in? Section 3.4. Just so you can see the homework, so you can see what it's going to look like. Look on page 260. We're not going to even do these problems unless you have one you want to look at. Page 260. It looks a lot like the way I would set up a test. Incredibly enough. I warned you, like on page 260, this is section 3.4, number 5 through 10, they give you problems, but all they want you to do is list out the possible rational zeros. So that's where on the test, I would feel free to say like 12x to the 8th minus 38x to the 5th, throw a plus at the end 80 or something. And you just have to make the ratios of all the factors do. Right? Now if I asked you to factor that thing, that would be forever. And then what's the point? You get one problem done in 2 hours. What's good?
Like that one. The one that you gave us is good.
Oh, that one?
Yeah.
Is that a suggestion you want me to use that one?
Yes.
All right. Go ahead.
Oh, you can use it as an upper bound.
Yeah, upper but you know, I obviously can't give you one that's just crazy. Because like somebody pointed out, if you're unlucky, and all of a sudden Indiana Jones and the Last Crusade came to mind because you picked wrong. If you pick wrong, you could go down this path that takes you forever to finish that. I understand that, especially when you have fractions in there and plus or minus. So obviously the problem I'm going to give you, I'm either going to make it ugly and give you some hints, or I'm going to make it not so ugly, but still want to see with no hints. And I'm not taking suggestions on how to make the test, so we'll see. It's going to be one of those two. On page 265 through 10, it just asks you to list the rational zeros. Don't try to do anything else. That's all they want.
Page what for?
Page 260, section 3.4.
What for?
5 through 10. And then 11 through 14 are visual examples. So they have the graph that's already graphed. And you can see that there are roots, and you can look at the problem and see what the possible zeros would be. And then they ask you to look at the graph and see what actually came out to be. Not a big deal. 15 through 46 is the meat and potatoes of this section. Right? It's here's the function, attack it. List all the zeros. Cool? Yeah, do everything to it. 47 through 56, the only reason they gave that its own section is to warn you that you might need quadratic formula like that last one we did. It's gone now, but remember when we got 2 plus or minus root 3 or something like that? With me? Let's see. 57 through 64 adds on. They want you to graph it. Don't just stop when you find the zeros. They want you to go further and graph it. So then you can use multiplicity. You can use all the other stuff we talked about before. So realize this. Somebody else realized this earlier. This is all just about finding the zeros. And that's step one in graphing something, right? So if you really want to get into how evil I could be, but I'm not going to be, you know, this monster ugly thing where step one to graph it takes you forever because you have to find the zeros. And that's just step one, because then you got to talk about end behavior, you got to talk about does it touch, does it go through, to finish out the graph. Okay? Yes?
And like if we
So
put
in
the
section
like
7,
this function in the calculator and graph it when we pick minus zeros, will we get the zero or no?
So, you know, I'm not,
Just to check.
I consider doing this, I'm not going to do this, I'm not going to like collect your calculators at the door and then give them back to you if you when you're done with certain problems. You can be very smart about how you use your calculator. I'm not going to ask you to use it all the time, but you can get a feel ahead of time. You still got to show me the work.
Yeah, but like it, so you can check or
Yeah.
something.
So you can guarantee that I'm going to have some questions that force you to do
The actual
certain
work.
things so I can make sure you can do it. Yeah. All right. Then they have use Descartes' rule of signs. And then here's a good problem, 71 through 74. Show that the given values are upper and lower bounds. So that's kind of nice. Because they give you options. They say try 3 and -1. Show that those are upper and lower bounds. So just test, do you know how to interpret what you get? Yeah, are they all positive? And the other one, do they alternate? Right? Okay. Blah, blah, blah. 3, 5 is complex numbers. That's where you're going to, and I didn't do this on the board, but I hope to God we can all add complex numbers. Like 5 plus 8i plus 7 minus 2i, just like terms.
which one was it? Number 5?
Section 3.5,
45, 268.
page 268. So this section should sort of be, really should be a breath of fresh air for a little bit in between all the graphing now, right? Should be. Okay.
They're not there.
Really?
Is it draft one?
Graph what?
In engineering.
No, we don't.
But there exists.
That's not this class.
Maybe
Have you guys heard of fractals? If you go to my website, there's actually a fractal up there. Fractals are used in art a lot. They, yeah, a lot of things we see, it's funny, fractals are used in places you don't even realize they're used. But fractals, some fractals are graphs of imaginary numbers. And the funky thing about graphs, not imaginary numbers, but imaginary valued functions. So the cool thing about graphs of complex numbers is you have to use color. The different colors, if it's black, that means that's the most imaginary. If it's not, if it turns lighter shades and it becomes different colors, that means it's less imaginary, more real. So you end up with this really cool looking thing. Trust me, it's neat. Anybody ever heard of Mandelbrot Sept? Just me. It's not something that's common knowledge, but it's one of the most famous images of a graph of a complex function. And it's
Like
really
they
neat.
try
And
to
the
say-
thing with fractals is the more you zoom in on them, any part you zoom in on, it repeats the shape of the whole thing. Infinitely long. And you just keep zooming in and it's going to repeat the shape of the whole thing forever and ever and
It's
ever.
like the Fibonacci sequence.
Fibonacci can be used in conjunction with complex numbers, but they're not like directly related. And then finally, section 3.6. All section 3.6 does is it adds in, you do all the same stuff we were doing, it just adds in the possibility that some answers could be complex. So 3.6 to me is more like a review section, really. So let me ask you this question. This is a question we haven't tried yet. Can you create a function, polynomial function with real coefficients that has 3 and -I as roots? And I will tell you straight up, there's an evil part of this problem.
Or we just
Three,
start back
three
up.
what? Three what?
3 and negative I.
Just like x minus 3.
Okay, good start,
How much is this?
right? It has to have an x minus 3, doesn't it?
Yeah.
If 3 is the 0 of this thing, if 3 is the root, it's got to have x minus 3.
And x plus negative 5.
It's got to have x plus I. Now what sucks if you stop right there? Are you going to have real coefficients?
No.
No, you're going to have ix, aren't you? And what's wrong, what's kind of
It
wrong,
should be x
but
minus
really it's just evil.
x minus I.
Yeah, if there's a negative I root, there must be its complex conjugate. There must be a plus I root also. This would be how do complex numbers show up? In pairs. So if negative I is a root, then so is plus I. So that means there would be a.
X minus I as well.
Now when you multiply those, that's a difference of squares looking dude, right? The middle term's going to cancel. No more complex coefficients. You with me? So now I get x minus 3. X squared minus I squared is.
Minus 1.
Yeah, minus I squared is minus negative 1 is plus 1. And then you can multiply that through and be done with it. Cool. So there will be a couple in the homework that are kind of like this. I don't know where I'm at. There will be a couple in the homework that have questions like create the function with roots of this and this and this. And if they list one complex number, you better include its conjugate for this to be real coefficients. Okay. So I think that might be enough. So let me just give you a warning. Not a warning. A little preview. Section 3.7, I've already heard this word come up earlier, is where we start looking at functions that have asymptotes. We're going to start looking at rational functions. They could have vertical asymptotes, horizontal asymptotes, slant asymptotes. Oh yeah, we'll find out.
I have a question.
Um, somebody remind me, when's the next test?
Next Wednesday.
Wednesday was next.
Oh, cool. So let's have a quiz next week. On that?
The 26th.
26, okay.
That's next. That's next week.
That's Wednesday.
19, 26, yeah, you're right. So 7 days from this Wednesday.
So we'll have a test on.
So we'll do a quiz this Wednesday. I thought it was going to be today. Just got 2 days of respite. Give me a break. So on Wednesday we'll have a quiz. It's only going to go up through, we'll do 2.7 through 3.3 because I think, yeah. 2.7 through 3.3. So it's not going to include any of this finding rational zeros. It's going to go inverse functions up to synthetic division. 2.7 up to 3.3. Oh, did I not?
Huh? No, you did this one, but really. Like,
Oh yeah, yeah.
the
This
first day
now
after that,
now
yeah.
what we did. Yeah, you're right.